does that scale read? Under various circumstances, of course, I'm going to talk about when the elevator is accelerating downward, when it's accelerating upward, and so on. So there will be various cases. But first of all, you need to think about what the bathroom scale is measuring in the first place. You say, well, it's measuring the guy's weight. Well, actually, it doesn't have access to the guy directly. All it knows is that there's some force acting down on it, right? So what it actually measures, the bathroom scale, is the force acting down on it. Or, what is the same thing by Newton's third law, the force that it's exerting up on whatever is above. In other words, the normal force. So you stop to think about it, what the scale is actually measuring is the normal force. One way of thinking about it is that it's measuring the normal force acting upward on the person. That's the way to get it. You get your hooks in this problem. The normal force person exerts a force downward on the scale exerts an equal and opposite normal force upward on the person, and that's what the scale is going to read. So, hey. The first case, suppose that the elevator is at rest. Not moving at all, it's stopped at the third floor. What is the reading on the scale in that case? Well, we need to draw the forces that are acting on this guy. Today, forces are red. So, tell me, what forces act on this man? The weight, of course, so mg acting down. What else? The normal force exerted by the scale upward. That's the thing we want to get. Want to know what it is. What else? Good. Nothing. That's it. So the guy is not moving. Those forces must balance, and minus mg equals 0. That tells me that n is equal to mg. That's what the scale measures if the elevator is not moving at all. It measures mg, which is the guy's weight, which of course is exactly what we wanted. That's the normal circumstance. Second possibility, suppose that the elevator is going up or down at a constant velocity. So it's somewhere between the third floor and the seventh floor, and it's just going up at a constant rate. In that case, what's the acceleration of this guy?
Zero.
Zero. He's not accelerating, and therefore the net force on him again must be 0. So this time 2. N is equal to mg, and this scale records the person's weight. Right? No force on him. Why? Because he's not accelerating. Yeah, but he's moving up. I don't care. He's not accelerating. C. Elevator accelerating upward. Okay. In this case, Newton's second law says that the net force acting on him in the upward direction, let's draw him in the upward direction because that's the direction of the acceleration. The net force in the upward direction, n minus mg, n up, mg down, that net force is no longer equal to 0 because the guy is accelerating. It's equal to his mass times his acceleration. Whoops, not a g. Okay. Make sense? So we're talking now about a brief moment Just after you step into the elevator on the 3rd floor and it's at rest, you punch the button and it starts going up. Well, it's got to accelerate to get up to the velocity it's going to rise at. During that moment, it's accelerating upward. M minus mg is equal to m times a. If I pull the mg over to the other side, this tells me that n is equal to mg plus ma. Right? So the scale now reads somewhat larger than mg, larger than his weight, and he feels kind of heavy. It's like somebody had cranked up the value of g. That's not what actually happened. It's just that the person was now accelerating, and therefore the normal force has got to be larger because it's pushing him upward. Finally, how about the elevator accelerating downward? That could be either that you've arrived at the 11th floor now and it's going to come to rest, so it's slowing down, or it could be that you're on the way down from the 11th floor and it's speeding up. I don't care. In either case, how should we work it out now? Now there's a net acceleration in the downward direction. I'm inclined to write the forces all in the downward direction now. mg minus n is equal to the mass of this guy times his acceleration in the downward direction. What does that tell me? If I pull the n over to the other side and the ma over to the left side, it would say n is equal to mg minus ma. In that circumstance, where the elevator is accelerating downward, the scale suddenly reads somewhat less than the person's weight. Indeed, what if the elevator accelerated downward exactly with the acceleration g? That would be free fall. You can do that easily. Cut the cable on the elevator. In that case, what does the scale register? 0, right? Then you have mg minus mg, and you get 0. That's what we call weightlessness. It's not that the guy was actually weightless, it's that the scale isn't recording anything because the guy is accelerating downward just at the rate of gravity, and therefore the normal force, which is what the scale actually measures, is now 0. Make sense? Yeah.
Would the free body diagram for all of them look like that?
Exactly. Yeah. I did switch the directions here just because acceleration in this case had been pointing up, and so it seemed sensible to call that positive direction. Here the acceleration was down, so it seemed sensible to call down in the positive direction. But the same two forces are acting always. It's just that they're not the whole story. In the first two cases, there's no acceleration, so that's the end of the line. In the last two cases, they are producing acceleration, either in the upward direction or in the downward direction. And the consequence is that the normal force, which, as it turns out, is what that scale is actually measuring, is larger or smaller, as the case may be. Make sense? Yeah.
Yes. So the positive direction is which one?
Positive, I use the positive direction upward for C and downward for D. If you don't like that, by the way, you could say, no, let's keep it positive always. Then how would I have written D? I would have said N, positive, minus mg is equal to m times the acceleration, but the acceleration is downward and the positive direction was upward, so if I'm talking about magnitudes, at least I would have to stick that in with a minus sign, and then it would come out exactly the same. Personally, but I'm not sure whether all physicists would do this, but personally, I usually scan the problem and find out which direction I think the acceleration actually is in, and then I call out the positive direction. I think that I make fewer sign errors by doing it that way, but it's maybe more consistent to decide once in your life upward is always positive for acceleration, and I'll put in the minus sign right after the acceleration. Okay, second example. Uniform circular motion. Here's a sweet model. It's actually on one of the owls for Wednesday. suppose that I have a table here, and it's a nice frictionless table. You can actually make, I don't know if you've seen these things, but air tables exactly the same as the air track, only instead of just along a line, it's a whole table, and it has these little jets of air all over it, and then you put a hockey puck on it, and it floats around on a cushion of air, like really nice frictionless surface. Well, I've got some object, actually, I'm making a hockey puck here, and it's going around in a circle on that frictionless surface, a circle of radius r. How does that happen? Because I've tied a little piece of string to it, and the string goes over here and passes down through a little hole in the table, and underneath the table, there's a mass that's supporting it here. This is a mass capital M, and the hockey puck has a mass little m, and it's going around in a circle of radius r. Practice, actually, you don't want that to have go literally through a hole, because that would produce a lot of friction on there. They can actually make these things a little pulley on a swivel so that it's a nice frictionless way that the string has of getting down under the table. Okay, attached to a string through a hole. Down to a mass m hanging below. So, is the scene clear? Imagine what's happening, and that thing is going around in a circle. I tell you it's going around in a circle, and the question is, how fast is it going? I think you can imagine physically, if it was going around in a nice circle like that, and I was dissatisfied and I hit it with a hammer or something, I've got it going faster than that, what would happen? It would no longer go in a circle. It would swing out in a larger and larger spiral, and it would lift up this mass, right? Conversely, if there was some friction acting on it or something, so it got too sluggish, it would spiral inward, and this mass would drop down. But I'm telling you, this is frictionless, and it happens to be going just exactly the right speed so that it keeps going around in a circle, and it's our business to find out what that perfect right speed is. There's the scene. Okay, let me draw the two bodies in question here are, of course, the hanging mass, M, and the hockey puck, little m. Let's see what forces act on those. First of all, this one here. Capital M. Weight acting downward for sure, so capital M times G. Somebody said the other one, tension, pulling up, that's the tension in the string. Anything else? No, that's it. How about the hockey puck here? What forces act on it?
Centripetal. Centripetal.
Centripetal force. What force is that? Tension. Very good. Okay. I hope you caught that, because that was a beautiful sequence of questions. She said, centripetal force. Well, when centripetal force doesn't tell me what the force is, that's, in a way, it's the consequence of the force is that you're going to get centripetal acceleration. It's, if I say, what's the force, I want to know somebody's pulling or pushing on this. Be very careful about that, because some people would put in the centripetal force as though it was a separate entity. There is a centripetal force here because there's a centripetal acceleration. That centripetal force is the tension. It's not two different things. It's like, I sometimes think it's like the difference between the money you spend and the merchandise you got. They may be equal, at least they were in the good old days, but they're not the same thing, right? If you go into a store and you buy an apple and somebody says, that apple was 50 cents. Well, of course, the apple wasn't 50 cents. The apple was an apple. I paid 50 cents. I got an apple. They happen to be equal in value. But that's Newton's second law. It says F equals ma. The A is the apple you got. The F over m is the money you paid for it. But they're not both forces. One's the force, one's the acceleration that you got for the force. Yeah.
mv squared over r, that would be what the formula for the force.
That would be the formula for the force, but it is not the force. That's the mass times acceleration. That's the right-hand side of Newton's second law. When I'm drawing forces, I want to know just what forces act. I'm not even thinking about the consequences of those forces, not even thinking about the acceleration. See, part of the problem is that you know too much, so you're thinking ahead of the game. Right now, I just want forces. I need to know what pulling or pushing on that thing. So, tension. Good. Pulling along in this direction, in this case. What else? mg, of course, the weight acting down, mg, and normal force acting up. By the way, in this particular problem, those two are completely irrelevant because they just cancel each other in the vertical dimension. It's the horizontal dimension I'm really interested in. What else? Good, that's it. Now, today, acceleration is green. I'm going to draw in here the direction of the acceleration and the amount of the acceleration, which you quoted for me, since this thing is going in a circle, the acceleration is v squared over r. But that's in green to remind me that's not another force, that's the consequence of the force. Okay, now let's write down Newton's second law for each one. For the first one, the one here, T minus mg equals, you tell me. 0. How come? That one's not accelerating. Who said it's not accelerating? Well, what I said is that the little one goes around in a circle. And the consequence is that this one isn't moving up or down, right? Because it's attached to the same string. So you're right, the acceleration has got to be 0. And I secretly told you that when I said that the thing was going in a circle. So T minus mg is equal to 0. That tells me, if you like, that T, the tension, is equal to capital M times g. Now how about Newton's second law for this one? Well, in the vertical direction, n is equal to mg. Not too interesting. In the horizontal direction, it says T, the only horizontal force acting, is equal to mass times acceleration. Is this thing accelerating? You better believe it. It's going in a circle, therefore it is accelerating in the amount v squared over r. So this is m times v squared over r. Put these two together, the first equation coming from the mass down below tells me that the tension is capital M times G. The equation, Newton's second law applied to the hockey puck, tells me that T is also equal to mv squared over r. So mg is equal to little m times v squared over r. And I can solve for v. Let's see, multiply through by capital R, divide by m. So it's got give me v squared is equal to r mg over little m. Did I do that right? V squared is r capital M g divided by little m, and then to get the velocity itself, the speed, take the square root. So there's the formula for the speed that this thing must have if it's going around in a circle. As I say, if you give it a kick so that it's going a little faster than that, that means that the tension here supplied by mg is not enough to keep it going in a circle like that, and it spirals outward. Then, of course, this equation is no longer true, and all bets are off. In fact, you've got a much more complicated problem if you allow the bottom mass to be moving up or down, and the radius of the circle, therefore, to be changing. You might want to fiddle with that sometime, but it's waiting on my needs today. Okay, enough on that one. A few problem, sometimes in lab, I don't think you're doing that this year, but sometimes this is done in the laboratory as a way of measuring the centripetal acceleration. You know, we know that the centripetal acceleration is supposed to be v squared over r, but if you ever ask, well, how do I know that in the laboratory? Here's one way that you could do it. Find out what mass you need to produce a given velocity, or the other way around, for a given mass. Make the thing go in a circle by pushing it at the right speed, and then find out what that velocity is, and, and that will be a confirmation of the mv squared over r. Third example, a classic problem, banking of a roadway. You know, when a road goes around a corner, they typically tilt the roadway, bank the roadway. Why do they do that? In England, they call it camber, by the way. I was driving once in England, and I encountered this street sign, the most opaque street sign I have ever seen. It said, reverse camber. And it was about 5 miles later that I realized what that must have meant. Reverse camber meant that I was about to go around a corner, and for some reason it was banked in the wrong direction. Reverse camber is how they say it. Banked the wrong way. But why do you bank a road at all? Interesting question. Let's look down from above on the car going around a curve. I draw it as a circle, but it may be just a little piece of a circle, I don't care. Here's the car seen from above, and it's going along with a speed v. And the circle, let's say, is radius r. So, and we'll give it a mass. There it is. Because that's going in a circle, it has acceleration in toward the center, and that acceleration is v squared over r. Let's put that in right away. A equals v squared over r. So there's the scene viewed from above, huh? Now let me stick my eyeball right in front of the car and watch that car coming at me head on. The roadway is banked like this. Here's the car. Coming toward me. You can tell from the headlights. This roadway is banked at an angle theta, and it's my business to find out, first of all, really, in principle, why is it banked? And secondly, exactly what is the proper banking angle? What should the engineer have used in designing that road as the proper banking angle? So here it is with the car coming toward me, and of course it's going to be curving around like that as it goes around. Got a picture? Okay, you tell me what forces act on the car as it's going around that curve. Don't tell me mv squared over r. That's not a force, that's what you got for the force. I want to know about the forces that are acting on this thing. Gravity acting down. So, mg. Normal force acting perpendicular to the surface. Anything else? Well, maybe friction, but we're going to pretend for the moment that there is no friction. So this is a frictionless surface. It's a very icy day, and this road is slick as can be. And you're going around the corner like that. And now there is an acceleration. How should I draw the acceleration in green on this same diagram? Which direction does it point? Parallel to the ramp, down like that. Ah, everybody think that's right? I say this thing is going around in a circle, And the centripetal acceleration must point toward the center of the circle. So let's think where is the center of the circle this thing is going around. How about that? The center of the circle is over here. Very critical. I'm going to come back and talk about exactly that point in a moment. The center of the circle is actually, see, it's going around in a horizontal circle like this. Where's the center of that circle? Right over here. Not down the ramp, actually, but exactly horizontal. So there's the acceleration, v squared over r. Now I'm ready to write Newton's second law of motion on that. That was another great comment. And as I said, I promise I'll come back and talk about that a little bit more in a second that you were anticipating. So what does Newton's second law of motion say for this? Well, I've got motion forces in two directions here. I need to resolve those forces into components. Question: shall I do the components parallel and perpendicular to the surface, or shall I do them horizontal and vertical? I'm going to do them horizontal and vertical. How come? Because I happen to notice that the acceleration is horizontal, and it's useful to have the acceleration pointing straight along one of the coordinates. Why? Because otherwise I'm going to have to take components of the acceleration too, and I don't want to do that. If the acceleration is pointing directly in the x direction, let's say, then it doesn't have any y component and it's easy. But if I have to take components of A as well as components of the forces, that's a little bit nastier. Again, this is anticipating the point I'm going to make later on, but I'm going to do horizontal and vertical. So first of all, in the vertical direction, what do I see here? I've got mg acting down, and I have a component of n acting up. What component is that? This is the angle theta. It's the nearby side, so it's the cosine of theta that I want. So acting up is n cosine of theta. Acting down is mg. What's that equal to? 0. How come? Not accelerating up and down. Horizontal. Okay, in the horizontal direction, I see no component of mg. I do see a horizontal component of n, that is n sine of theta. And that must be what's providing the centripetal acceleration action. That force to the right is equal to m times a, where a is the acceleration in the horizontal direction, mv squared over r. See how it goes? So here's the vertical equation of motion. Here's the horizontal equation of motion. Now I want to put them together to find out what the angle is. I never said what the question was here. Question. What's the correct banking angle theta? That's what I want to find. So I've got a normal force in here, which I don't know anything about. I think I'm going to solve the first equation for n. Would that be all right? Take that down here. N cosine theta is equal to mg. So if I divide off the cosine of theta, I would have n is equal to mg cos theta. Now let me stuff that into this equation here, and the n's will be out of sight. So I get mg times sine theta from here over cosine of theta coming from n is equal to m times v squared over r. Well, the m's cancel out. That turns out to be a very lucky thing, as you'll see in a moment. I'm looking for theta. Here I have sine over cosine, so it's g tangent of theta is equal to v squared over r, or tan theta V squared over RG. That's the angle at which this curve should be bent. Now I got a couple of comments on this. First of all, let's go back to the question, why did they bank this curve in the first place? Well, to go around a circle, I'm going to have centripetal acceleration in toward the center. Therefore, I've got to provide a force in toward the center to accomplish that acceleration. I must somehow or other get a force in toward the center. Suppose that I had an absolutely flat surface here, and the car was horizontal surface, and the car was coming along like that. Who's going to provide a horizontal force to make that car go around in a circle? The normal force can't do it, straight up. Gravity certainly can't do it, that's straight down. It would have to be friction. Friction I could get in there, friction that would exert a force in toward the center, but friction is notoriously unreliable. It might be a wet day or an icy day. I don't want to have to rely on friction to do the job. If the friction was not sufficient, I'm going to go off in the ditch. Therefore, the idea of banking is actually ingenious. What's the purpose of it? Force the normal force. By tilting the road, I'm tilting the normal force over at an angle. That gives the normal force a horizontal component, just exactly what I want. So I have forced the normal force to give me a component in toward the center of the curve, which is exactly what I want. I don't need any friction in the problem at all. So I can go around that curve. In principle, you could go around the curve, a properly banked curve, without any friction at all. On a perfectly icy day, then you'd have no trouble. The normal force is pulling you around the curve, and you don't rely on friction. There is one small snag here, and that is that the correct banking angle depends on the velocity. Also on the radius of the curve, but that's fixed, of course. But it does depend on your velocity. So you've got to go around that curve at exactly the right velocity, otherwise it's not banked right for you. Well, of course, if you go a little bit too slow, then you're going to tend to slide down the hill, and you'll need a little bit of friction to keep you on the road. If you're going a little too fast, then you'll tend to slide up the bank, and a little bit of friction will hold you in the track again. So, but you're only requiring a little bit of friction to correct for the fact that you didn't go around there maybe at exactly the right speed that the thing was designed for. Yeah.
If it's very wide, does it work that the radius change goes in the right direction? And you don't need friction, you just swing out to a further radius where the V-squared
Oh,
will
gee, I
work
never
as
thought
that?
about that. Is that true?
I think it's
It's self-correcting?
I think it's a stable situation, but I'm not sure. It may be the wrong way, but I have a feeling it's the right way. So
That
that
could
if
well
you
be.
have one of these real professional racetracks, that's a wide track, and you come in wrong, you slide to the outside, you take up a greater R, which means a lower acceleration.
But they don't actually,
They got, well,
they
some
could
of them
also maybe have a
yeah,
curved
half
track.
pipes, I think, have some of that.
So that they're, very clever. I never thought about that. Right? Because
I
it's
think
true.
it's
As you,
stable as opposed to unstable.
How about that? Nifty. So if you did go too fast and you slid up the curve, you're now going around the curve that's a larger radius. Therefore, if required, you will have a smaller acceleration.
I think it works.
I think it works, yeah, very neat. One thing is nice about this formula, by the way, I pointed that out before, that the mass canceled out. So the proper banking angle is the same for a Mack truck and for a VW bug. That's a lucky thing, too, because otherwise I guess they'd have to have signs that say, around this curve, if your weight is so-and-so, then go at such and such a speed, if it's so-and-so, go at some different speed or something. Now, I want to come back to your point before, because, and actually, let me remind you of how I solved and how I analyzed last Friday sliding motion down an inclined plane. This is a different problem, but sliding down a frictionless inclined plane, what did I do? I drew the body like that, and then I put in the forces, and the forces were gravity acting down, normal force acting up, And in that case, I analyzed the problem by resolving the forces parallel and perpendicular to the surface. I don't know if you remember that, but I took the parallel and perpendicular components of mg, because in that problem, the acceleration really was down the slope. This always bothered me when I was first studying the problem. I couldn't figure out, when people are talking about sliding down an incline, they always resolve the forces parallel and perpendicular to the slope. When they're talking about the banking problem, exactly the same two forces involved, by the way. mg and n diagram looks almost exactly the same, but these turkeys suddenly were analyzing the forces horizontal and vertical and never told me why. Well, I'm telling you why. The acceleration in this case was horizontal. In this case, the acceleration was parallel to the plane. So it makes good sense in the sliding down an inclined plane problem to resolve your forces parallel and perpendicular to the plane. It makes good sense in the banking problem to resolve the forces horizontal and vertical. Does that make sense? But it's all key to the direction of the acceleration, which is why just for today I was drawing the acceleration in there carefully in green. Okay, friction.
We have it on videotape.
It's fun, 17 and a half seconds. Friction, kinetic friction. So suppose I have some object, here it is, nice rough object, and I shove it. Obviously, as it moves along, there's a frictional force on it. And that frictional force is obvious, it's always backwards as far as the direction of motion is concerned. It always opposes the motion. If I'm going toward you, the frictional force is back. And that way, frictional force that way. Always the frictional force is opposite to the direction of motion. So, block. Frictional force F, opposite to the direction of motion. So here's a picture of it. There's the object. It's moving along. Velocity is good. Moving along like that, and there's going to be a frictional force acting on it, always in the backward direction. I think it's pretty obvious that that frictional force is going to be larger if you squeeze the two surfaces together more. Isn't that right? If I lean on this, then the frictional force is pretty big. Now it's relatively small. How much, or actually another way of doing it, stick your hands together and rub them. If you really push hard together, there's a lot of friction. You feel it in the heat that's generated. So somehow or other, the frictional force, I think it's clear that the frictional force is going to depend on how tightly those two surfaces are squeezed together. In other words, on what the normal force is. In point of fact, it's usually the case that the frictional force is roughly proportional to the normal force. So we write it like this. F is equal to mu times n. I'm going to put a little k in here because for today, I'm talking about what's called kinetic friction or sliding friction when the two surfaces are sliding on one another. There's also static friction that has to do with a more complicated situation where the two are actually not moving relative to one another. That's, as I said, a little bit more complicated to analyze, and we'll talk about that on Wednesday. So today, I'm just talking about one surface sliding over the other. The frictional force is proportional to the normal force. The proportionality constant mu sub k is the so-called coefficient of kinetic friction. The mu is a Greek letter mu, small Greek letter mu. To distinguish it from a u, I put a huge old tail on it, which is a little bit of an exaggeration, but for my own purposes, so I don't confuse it with a u. The proportionality constant is called the coefficient of kinetic friction, or sometimes sliding. And what the value is depends entirely on the two surfaces. This combination here has a fairly large coefficient of kinetic friction, but if I polished up the surfaces and stuck some oil on there or something like that, then I would have a much lower coefficient of kinetic friction. It just tells you, sort of very roughly speaking, how rough the two surfaces are. So typical values. Could be, by the way, it's dimensionless because this is a force and this is a force, so it's just a pure number. Mu is on the order of 0.2 up to 0.5 or something like that, but it depends entirely on the surfaces. Folks, this is no fundamental law of physics. It's not a rule like F equals ma, or centripetal acceleration is v squared over r, or distance traveled at motion of constant acceleration is 1/2 at squared. Those are fundamental. This is a rule of thumb that applies pretty well to most surfaces, but you're not going to get any Nobel Prize for finding some error surfaces that don't obey that formula. The response would be, oh, so you've done funny kind of surface deal. I like to distinguish them because in physics we encounter some things that are bona fide laws and other things that we tend to use in exactly the same sort of way, but are not genuine laws at all. Ohm's law, if you studied electricity, is another example of something that's not really a fundamental law, it's just a rule of thumb that applies amazingly well to a lot of stuff. Okay, let me show you an example of friction. In fact, what I want to do now, somebody had asked me to go over the third OWL for today, I believe it is. So what I'm going to do is that same problem, but stick some friction into it. So we're up to example 4, I think. I don't know what the name of this is, but it's a surface like this, tilted at an angle theta. There's a box on here, and there's a rope attached to it, goes up and over a pulley, and over here there's another mass m. This is mass little m, and of course what I want to know is what's the acceleration of this system. The acceleration of this mass, let's say that this is a big heavy mass, this is going to accelerate down, this is going to accelerate up the slope, and I want to know what's the acceleration. You did it for a frictionless surface here, but now we're going to do it for a surface that has coefficient mu sub k, coefficient of kinetic friction mu sub k. So as that line is sliding up the plane, what are the forces acting? Well, I think I better draw the two subsystems separately. This one here, the hanging mass. Forces on it, weight acting down, capital mg, tension in the rope, pulling up, T. Okay, this one here, this mass, well, weight, normal force for sure,
Tension.
to the surface, tension,
Friction.
and friction now. Friction opposing the motion, so as it goes up the slope, friction is going to be back in that direction. And I guess that's it. This one, the acceleration is down. This one, the acceleration is up the plane. So that already has told me I'm planning to resolve the forces parallel and perpendicular to the plane, not horizontal and vertical. In fact, horizontal and vertical would be lousy here because there's only one vertical force in the problem. There are three things that are parallel and perpendicular. So, Newton's second law applied to this mass, capital Mg minus T equals capital M A. For this mass, I've got two dimensions to work with, parallel and perpendicular to the plane. So perpendicular, let's do that first. Perpendicular to the plane, what do you see acting there? N acting up, and pulling it back is this component of mg. What do I want, sine or cosine? Cosine, good. Zero, huh? It's not accelerating, perpendicular to the plane. Okay, parallel to the plane. That's along this direction here. Pulling up, I have T. Pulling back, I have F now. Of course, for your problem, the F isn't in there. And I also have, pulling it back down the plane, the component of mt. And that's equal to the mass of this object times its acceleration. I'm not going to have time to finish this, but let me put the last equation on the board. F, the frictional force, is equal to mu k times n, huh? So the frictional force is mu k times n. Do I have a complete solution on the table then? F is equal to mu k times n. N is equal to mg cos theta. So I can now stuff this frictional force, which I know, into there. I've got T from over here, and I can solve for A. Sorry, this is a lousy place to drop the problem, but the rest is algebra.